Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Semiconductor based optical sensors from the paper Semiconductor Materials and Devices. So let us see what we are going to learn in this module. First, we will discuss about the surface plasmon resonance, which is the basic phenomena in the optical sensors. Second, SPR-based optical sensors, including their sensing strategy, will be discussed. Thirdly, the semiconductor metal oxide thin film-based sensors will be discussed. So students, let us start with a basic introduction about the module. Optics plays a pivotal role in the field of data transmission, acquisition, information processing, and various other applications such as microscopy, spectroscopy, metrology, velocimetry, particle manipulation, etc. Nowadays, optics has received much attention in terms of wide range of instruments and tools which are available commercially. Hence, rapid advancement in the development of optical devices and systems leads to fast moving field of optical sensing and measurement. The optical devices are advantageous as compared to electronic devices due to the lack of direct contact, high spatial resolution, resistance to electromagnetic EM radiation, and relatively easy detection. But they also have few disadvantages, that is the need for the optical transducer to be transparent at the wavelength used for sensing, the use of labels, interferences, etc. Due to enormous advantages of optical devices, their demand and requirement has increased, leading to the development of various new optical devices having unprecedented high quality and rich functionalities. So, the last 2 decades, the remarkable research and development activity aimed at the realization of optical sensors for the detection of gases, chemicals, and biological species. First optical chemical sensor was based on the measurement of change in absorption spectrum towards the detection of carbon dioxide and oxygen gases. So, numerous optical methods are available for the realization of optical sensors, such as ellipsometry, spectroscopy, luminescence, phosphorescence, fluorescence, Raman, interferometry, white light interferometry, modal interferometry in optical waveguide structures, spectroscopy of guided modes in optical waveguides, grating coupler, resonant mirror, and surface plasmon resonance SPR. So, in all these sensors, the detection relies on measuring the change in refractive index, absorbance and fluorescence properties of sensing material, molecules in response to the analyte. Among the different methods, SPR is gaining a lot of attention and is increasingly being used for sensing purposes. The potential application of SPR technique for the characterization of thin films and monitoring processes at metal dielectric interfaces was recognized in late 70s. So there are huge number of research papers which are published on the application of SPR for the examination of biomolecular interaction. Theory of surface plasmon resonance. Let us first discuss about the plasmons. According to Drude model, the free electrons oscillates 180 degree out of phase relative to the driving electric field, due to which majority of the metals possess a negative dielectric constant at optical frequency, which is a consequence of their fairly high reflectivity. Furthermore, at optical frequencies, metals possess high electron density, that is around 10 to the power 23 per meter cube, which is comparable to that of a plasma. Since the mass of positive ions in metal is very large as compared to that of the electrons, so we can assume these positive ions to be fixed and the electrons as free particles. However, lattice as a whole remains electrically neutral. So when a weak electric field is applied across the metal, electrons are displaced slightly with respect to the ions. The Coulomb force between the electrons and ions pulls the electrons back and induces a restoring force. So the resultant of these two forces sets up the longitudinal oscillations amongst the electrons. The coherent and collective oscillations of these electrons are known as plasma oscillations. Just like we have the quanta of light waves, that is a photon, so the quanta of plasma oscillations is known as plasmons. Let us now discuss about the surface plasmons. Conductor metal dielectric interfaces, as shown in this figure, they are known to support the non-radiative propagating waves, commonly referred as the Zenek waves, Sommerfeld waves, or Fano modes. And in modern optics, they are called as surface plasmon polaritons, SPPs. Surface plasmons can be considered as quasi-particles originated by the coupling of surface plasma charge oscillations and the EM fields. Thus, surface plasmons are charge density oscillations of the free electrons of a metal, which propagate along the interface of a metal and a dielectric. So one can see the surface plasmons as the light waves restricted to the surface of a conductor. This field is an evanescent field, that is, it extends in both media while decaying exponentially, as shown in this figure. So due to the resonant response of the oscillating electrons, the field features a strong enhancement close to the surface. Surface plasmons are p-polarized waves and hence can be excited by a transverse magnetically TM polarized wave. And the schematic of the metal dielectric interface supporting a surface plasmon mode is shown in the figure B. So changes to the dielectric environment in contact with the metal surface strongly alters the resonance condition. Let us now discuss about the excitation of surface plasmons. For the excitation of surface plasmons, the resonance condition, that is the matching of wave vectors of the incident light and the surface plasmon wave SPW, should be satisfied. So this figure shows the dispersion curves of the direct light and surface plasmons at metal-air interface. In dispersion curve, only the real part of the wave vector is shown, and the decaying nature of the surface wave along the x direction has been neglected. So when omega is less than omega p, the excitation of surface plasmons is termed as non-radiative surface waves and have been shown by red line in this figure. Now when omega is greater than omega p, metal is transparent and the surface plasmons are radiative surface plasmons as shown by blue line in this figure. So the green line is correspond to the dispersion relation for the light traveling in air. So for a given omega, the wave vector of surface plasmons is always higher than the wave vector k0 of light in vacuum. Hence, the wave vector of the light incident through a dielectric medium is always less than that of the KSP at the metal dielectric interface. This means that the direct incident light cannot excite the surface plasmons on metal dielectric interface at any frequency unless special techniques are employed to achieve phase matching. Thus, to excite the surface plasmons, the wave vector of the incident light should be increased over its free space value. So, various approaches are available to provide this additional wave vector component to excite the surface plasmons. That is, high index prism, grating and optical waveguide. Prism coupling. The method used in prism couplers to enhance the momentum of an optical wave to allow the coupling to SPW is the attenuated total reflection ATR method. In this method, the optical wave is totally reflected at the interface between a prism and a thin metal layer. So optical wave evanescently penetrates through the metal layer and excites a SPW at its boundary. As observed from the figure shown on the slide, the wave vector of surface plasmon KSP for the metal dielectric interface is always greater than that of the incident light k0 in air, as discussed earlier. So when a light is incident through the prism of refractive index Ng, the wave vector of the incident light is increased by a multiple of Ng and is given as Kg equal to omega by c root of epsilon g, where epsilon g is the dielectric constant of the prism. So the wave vector of the evanescent wave KeV corresponding to the incident light wave and passing through at an angle theta is equal to the lateral component of the wave vector of the incident light wave passing through the prism Kg. So KeV equal to Kg sin theta equal to omega by c root of epsilon g sin theta. So the propagation constant of the surface plasmons at metal dielectric and metal interfaces is given by KSP metal dielectric equal to omega by c multiplied by root of epsilon s by epsilon m plus epsilon s, and KSP prism metal equal to omega by c root of epsilon m epsilon g by epsilon m plus epsilon g, where metal dielectric and prism metal represents the KSP along the metal dielectric and prism metal interfaces respectively. And all these are shown in the figure shown on the slide. Epsilon g is the dielectric constant of the prism. Epsilon s is the dielectric constant of dielectric media. Surface plasmon wave is excited only when KeV equal to KSP at similar frequency. This figure shows that the KeV intersects with KSP at m/t at many points for different values of theta, brown and green curve. So corresponding resonance conditions for KeV equal to KSP m slash d may be represented as omega by c root of epsilon g sine theta resonance equal to omega by c root of epsilon s epsilon m by epsilon s plus epsilon m. This implies that the fulfillment of the resonance condition is dependent on the frequency omega and the angle of incidence theta of the light beam. It is interesting to note from this figure that KSP P slash M for the prism metal interface red curve does not even intersect with the maximum value of KeV brown curve at any frequency. This indicates that SPW cannot be excited at prism metal interface for any arbitrary value of theta or omega. So the KSP m slash d is highly dependent on the refractive indices of the metal and dielectric media, and any changes in the refractive indices results in the shifting of the resonance condition, which is the property of the surface plasmons used for sensing applications. Surface plasmon resonance SPR. SPR phenomena can be understood by the resonant transfer of energy from the incident optical wave to the surface plasmon wave at the metal dielectric interface that leads to the excitation of surface plasmons. So, in order to excite the surface plasmons in a resonant manner, the incoming electron or light beam, visible and infrared typically, has to match its impulse with that of the plasmon. So, in the case of p-polarized light, polarization parallel to the plane of incidence, the resonance is possible at a given lambda and theta, that is the incident angle, by passing the light through a block of glass in order to increase the wave number and impulse. So when the condition of resonance is met in the system, the energy of the incident light wave, it is absorbed, and the energy of the reflected light is reduced. So if the frequency of the incident light, it is kept fixed, the reflectance shows a sharp dip in resonance due to the transfer of energy to the surface plasmons, and its monitoring could be used for sensing processes. SPR can be studied by varying the angle of incident of light, which is the angular interrogation. Secondly, wavelength of light, that is the wavelength interrogation. Thirdly, the phase difference between S and P polarized light, phase interrogation. And fourth is your intensity of reflected light, intensity interrogation. SPR based optical sensors. The optical sensors based on SPR, they have a great growth due to various advantages, having wide range of operative parameters and high stability. So the basic principles of SPR sensing, they are explained in the following sections, along with the defining the main parameters to be considered to characterize their performance. Let us first discuss about the SPR sensing strategy. The SPR optical sensor composed of an optical system, a transducing medium which interrelates the optical and biochemical domains, and an electronic system supporting optoelectronic components of the sensor for data processing. So optical system detects the change in the refractive index of the system corresponding to any change in the quantity of interest. So the transducing medium transforms the change in the quantity of interest induce the changes in the refractive index, which may be determined this by optically interrogating the SPR. The optical part contains a source of optical radiation and an optical structure having sensitive functional layer in which SPW is excited and interrogated. The optical system and the transducing medium affects the sensitivity, stability, and resolution of the developed sensors to a great extent. The primary parameters reflecting the performance of the sensor includes its selectivity and response. Since surface plasmons are highly sensitive to the changes of the refractive index in the vicinity of the surface, they are widely recognized as a suitable sensing probe. The SPR sensors exploits the properties of surface plasmons for the detection of analyte by optical means. Among optical sensors, SPR technology is appreciated for the possibilities of extreme miniaturization and integration and for being a label-free technology. The principle can be exploited for different applications, both for physical and chemical biosensor as shown in the figure below. SPR sensors performance parameters. The performance of a sensor is evaluated in terms of four parameters, namely sensitivity, detection accuracy, figure of merit, and response time. So for the best performance of a typical SPR sensor, the value of these parameters should be as optimal as possible. First, we'll discuss about the sensitivity. In the case of angular interrogation, the resonance angle theta resonance is determined corresponding to the refractive index of the sensing medium Ns or the corresponding variation in the content of stimulus. So if the resonance angle is changed by delta theta resonance by delta lambda resonance for a change of delta Ns in the refractive index of the sensing medium due to delta Ns change in stimulus content, then the sensitivity of the sensor is S theta equal to delta theta resonance by delta Ns or S theta equal to delta theta resonance by delta S. Larger the shift, higher the sensitivity of the SPR sensor. So for surface functionalized SPR bio and chemical sensors, the sensitivity depends on effective refractive index change and surface refractive index change caused by surface interaction binding. Let us now discuss about the detection accuracy DA, which is defined as how accurately and precisely a system can detect the change in a sample. So for surface functionalized SPR, bio and chemical sensors, the sensitivity depends on effective refractive index change and surface refractive index change caused by surface interaction. So smaller is the width of this SPR curve, larger is the detection accuracy. So the detection accuracy of the SPR sensor can be defined as the reciprocal of the width FWHM of the SPR curve corresponding to 50% reflectivity or normalized output power. If delta theta SPR be the full width half maxima of the SPR reflectance curve, then the detection accuracy of the SPR sensor can be written as TA equal to 1 by theta SPR. Let us now discuss about the detection accuracy, which is defined as how accurately and precisely a system can detect the changes in a sample. Figure of merit. Figure of merit FOM of the SPR is defined as the ratio of the sensitivity S and the width FWHM of the SPR curve. That is, F dou M is S by FWHM. And the response time is the time taken by a sensor to approach its true output when it is subjected to its input is termed as response time. So if the response time is short, then the sensor is better. In the case of SPR sensor, how quick the SPR dip changes its position to a stable point with the change in the sensing samples in the vicinity of sensing surface defines the response time. Apart from these, other sensor parameters which are important for the commercialization point of view are the shelf life, reusability, miniaturized size, cost, etc. Semiconductor metal oxide thin films for sensing applications. In the past few decades, semiconductor metal oxides have emerged successfully as a new class of materials that can justify and satisfy the three basic requirements, that is sensitivity, stability, and selectivity for a good sensor. So metal oxides with improved kinetics of electron transfer, chemical stability, good biocompatibility, and high adsorption capability pave the way to make desirable surroundings for the immobilization of biomolecule and better biosensing features. Although polymers and other nanomaterials do show the promising results that they lack in terms of stability and selectivity. It is easier to tune the electronic properties of semiconducting oxides and the sensitivity can be enhanced. Also, their novel properties like high surface to volume ratio, low toxicity, better solubility make them a potential candidate for different types of sensor, gas, bio, optical. Since then, a lot of work has been reported on the detection of various gases with better stability, sensitivity, and selectivity using various metal oxides, including tin oxide, tungsten oxide, titanium oxide, cerium oxide, silicon oxide, etc. So, out of these metals, tin oxide and tungsten oxide are extensively used for gas sensing applications and shows excellent sensitivity and stability. The most popular gas sensors are based on the conductometric detection techniques, where material engineering by adding other metal oxides to the hot sensing oxide material is necessary to obtain the desired high sensitivity, selectivity, and operating temperatures. Thus, SPR gas sensors using tungsten oxide and tin oxide sensing layer may be attractive for room temperature operation with enhanced sensitivity and selectivity towards a desired gas. Similarly, for biosensing applications, different metal oxides including copper oxide, nickel oxide, cerium oxide, zinc oxide, tin oxide, zirconium oxide, titanium oxide, etc. have been employed as matrices. So we can enhance the sensitivity of SPR sensors. Let us now discuss about it. The sensitivity of the SPR-based sensors is an important parameter. To achieve high sensitivity of SPR sensors, the optimization of optical structure is essentially required and suitable design parameters are needed. So the resonance condition depends upon the refractive index of the prism, the dielectric constant, and the thickness of the metal and the sensing layer, and the wavelength of the incident light. So in addition to the above factors, FWHM of the SPR reflectance curve representing the absorption losses should be minimum for the realization of highly sensitive SPR sensors. However, long-range surface plasmons LRSPS, they have a strong coupling and enhances the SPR sensor resolution significantly. Therefore, attempts have also been made to explore the LRSPR sensor. So students, let us summarize what we have learnt in this module. Firstly, we discussed about the theory of surface plasmon resonance, including the concept of plasmons, surface plasmons, excitation of surface plasmons, and surface plasmon resonance. Secondly, the SPR, which is the basic phenomena involved in optical sensors. It was discussed, including their sensing strategy. Thirdly, we discussed about the semiconductor metal oxide thin film based sensors and the ways to enhance its sensitivity. Thank you.